Hello. Today we'll continue our itinerary in Laplace transforms with two problems from homework 12, right? So let's try to state the requirements in this homework. So let's assume that f of t transforms into big F of s, which is the integral from 0 to infinity e to the minus t f of t dt. So the first problem requires the following. Find the transform of if you multiply the input function by an exponential. So find the Laplace transform, not of f of t, but the exponential e to the power a t f of t. So let's do the solution here. So Laplace transform of e to the power a t f of t, there's a function for which we want to do the Laplace transform. By the definition of the Laplace transform is integral from 0 to infinity e to the minus st times this function which you want to transform e to the power a t dt, which will be integral from 0 to infinity. Let's combine those two exponentials to 1. So e to the power minus quantity s minus a times t. Sorry, I forgot to put here f of t. Because we want the transform of this e to the power a t f of t. So the transform of e to the power a t f of t is integral from 0 to infinity e to the minus st e to the power a t f of t. There's the function we transform. And then combine the two exponentials into 1 e to the power minus quantity s minus a times t f of t dt. And if you look at this is exactly as a Laplace transform, normal Laplace transform, only the normal Laplace transform is e to the minus st f of t dt. So what's the difference? Instead of e to the minus st, we shift the variable s from s to s minus a. So this would be just Laplace transform of s minus a. That's exactly what we wanted to prove, right? So basically the conclusion here, let's write down the conclusion. If f of t transforms into big F of s, then e to the power a t f of t transforms into f of s minus a. Right. So that's one way to find the inverse transform. If you want to find the inverse transform of f of s minus a, multiply by e to the power a t, the inverse transform of big F of s. And there was one other problem there. Okay, let's see another one. What's the Laplace? This is very useful for solving differential equation with Laplace transform. Laplace transform of derivatives. Laplace transforms of derivatives. So again, if let's suppose that f of t transforms into big F of s. What will be a transform of the derivative? So find the Laplace transform of f prime. That's what I'm going to do next. Okay, so let's do the solution. Laplace transform of f prime of t is integral from 0 to infinity e to the minus st f prime of t dt. Okay. And now let's try to do integration by parts, in which u is e to the minus st and dv is f prime of t dt. U equals to e to the minus st, dv equals to f prime of t dt. So we have a specification of integration by parts. Now let's switch the d from u to v. So du is minus s e to the minus st dt, and v will be f of t. So these are specifications for integration by parts. So what's the integration by parts saying? is uv from a to b, from 0 to infinity. So uv means e the minus st f of t vertical bar from 0 to infinity minus from 0 to infinity, limited infinity minus the value of 0, right, for that matter. Minus integral from 0 to infinity of v du. V du. So we get du is minus s e the minus st. A d is f of t dt. Okay. We'll come back to that integral, but let's first of all concentrate on this difference. So what would be this one? Limit at infinity. Okay, so limit at infinity minus value at 0. Okay, let's see limit at infinity. Now, in any case, for s large enough, this exponential, negative exponential beats the potential exponential growth of f of t. Because even if the function which is transformed by using Laplace transform has Laplace transform, the exponential growth is bounded by some major exponentials. So cannot go farther than some exponential growth. So for s large enough, this will be 0. So for s large enough, 0 for s large enough. For s large enough. What about the value at 0? The value at 0, e the minus s times 0 is 1 f of 0. So f of 0. So basically, the whole difference for s large enough, this would be minus f of 0. And what about this one? Minus and minus is plus. So we don't really care about 2 minus here. So s is a constant, take the constant in front. S times integral from 0 to infinity, e the minus s still f of t dt. Which is exactly the Laplace transform of the normal function f of t. So this will be s big f of s. So what is the outcome? So what's still standing? We got s big f of s, and then put like using columns. S big f of s, and this one still stands. So what's left on the board? S big f of s minus small f of 0. So that's the formula for the Laplace transform derivative. So let's write down, keep the fruit of the work and erase the work. So what we got here? So Laplace transform derivative is s big f of s minus small f of 0. S big f of s still stands, minus small f of 0 still stands. So that's the final result for Laplace transform derivative, and we just proved it. For example, so let's see, normally from now on, more and more the differential equation is Laplace transforms. The unknown function is x of t. So the independent variable is t, the unknown function is x of t. So for example, if small x of t transforms into big X of s, then small x prime transforms into what? S big X minus small x of 0. What about x second? Multiplied by s, the previous line here, x second transform is s squared big X minus s small x of 0 and small x prime of 0. We can continue as much as we want. X third transforms into, multiply this by s and subtract the next derivative at 0. So s cubed, big X being big X of s, x cubed x minus s squared small x of 0 minus x small x prime of 0 minus small x second of 0. It's simple. So we got now the Laplace transform of subsequent series of derivatives. Okay, there is one more listed problem there. So exercise 3 from the homework. So let's see, we got here, if the Laplace transform of f of t is big f of s, say small f of t again, transforms into big F of S. Find the Laplace transform of T F of T. Find the Laplace transform of T F of T. So far we discovered how to do the Laplace transform if we multiply the input function small f of t by an exponential. This was the first exercise today. Now we don't want to multiply by an exponential, we want to multiply by a t, right? By a polynomial. Right? So what's the Laplace transform of t f of t? Okay, so let's write down what does it mean. Laplace transform of small f of t is big F of s. So big F of s is integral from 0 to infinity e to the minus st small f of t dt. That's by definition. Now, the idea here is to take the derivative with respect to s to the left and the right. And to the right, apply the formula we discussed in our previous lecture, how to differentiate with respect to s as a parameter in an integral. So now we'll get here left-hand side derivative with respect to s equals to right-hand side derivative with respect to s. Left-hand side, right-hand side. What will be left-hand side derivative with respect to s? It's clearly easy. It's f prime of s, big F prime of s, equals to how differentiate an integral with respect to the parameter s. Well, differentiate inside with respect to the parameter s is only d over ds times integral from 0 to infinity e to the minus st f of t dt, which is differentiate inside there's the formula for differentiate with respect to the parameter we discussed last time, is integral from 0 to infinity minus t e to the minus st small f of t dt. Because d over ds of e to the minus st is minus t e to the minus st. Okay, so let's pull the minus from here to here. So we'll get minus f prime of s. So therefore, minus f prime of s equals to integral from 0 to infinity e to the minus st times t f of t dt. So what is this? Is exactly the Laplace transform integral from 0 to infinity e to the minus st of this function. That's the Laplace transform of t f of t. So it's just like magic. Laplace transform of t f of t turns out to be minus the derivative of the Laplace transform of small f of t. So conclusion, the Laplace of t f of t is minus f prime of s. This is the conclusion. Okay. Okay, so let's try to put those things to good use, right? Again, part of the latest homework, right? So let's do some points on the latest homework. Application of these formulas. So let's find the Laplace transform of the following, and the real consequence of what we will find will be intrinsic. So find the Laplace. You want to prove that. So prove that the exercise 1 here. Prove that t over 2k sine kt transforms into s over s squared plus k squared squared. How to do this? So that's what we want to prove here. Prove that t over 2k sine kt transformed into s over s squared plus k squared squared. What is the consequence of this? As a consequence of this, L inverse, the inverse transform of s over s squared plus k squared squared equals to t over 2k sine kt. Okay, so let's see. Here's the solution of this based on the formula we discussed so far. We already know that, so we already know that sine kt transforms into k over s squared plus k squared. Now apply, so this small, like treat like a small f of t, big f of s. So let's find apply the formula for the what capital multiplied by t, the input function in the Laplace transform. So for this one, we get t. So therefore, t sine kt will be transformed into minus the derivative of this. So minus k over s squared plus k squared derivative with respect to s. Derivative with respect to s. So which should be what? Minus k is a constant. Here, if you differentiate 1 over s squared plus k squared, is like the derivative of the chain rule for 1 over u. It's minus u prime over u squared. So minus 2s over s squared plus k squared squared. So minus and minus is plus. We'll put here 2k times s over s squared plus k squared squared. Okay, so because of the linearity, divide by 2k left and right. So by linearity, 1 over 2k t sine kt, divide the left hand side by 2k, divide the right hand side by 2k, transforms into s over s squared plus k squared squared. So 1 over 2k. So we got important things. So important conclusion. 1 over 2k, or if you have t over 2k, just to be more compact. T over 2k sine kt, t over 2k sine kt, right? Like exactly what you wanted here, transforms into s over s squared plus k squared squared. Implicitly, the inverse transform of so the transform of the left is the right, the inverse transform of the right is the left. So the inverse transform of s over s squared plus k squared squared is t over 2k sine k. So we got one of those two important formulas. Okay. Number 2. Find the okay, so let's see. Find the following formula. So 1 over 2k cubed times sine kt minus kt cos kt transformed into, and this is the other partial fraction with the square at the bottom here. So 1 over 2k cubed sine kt minus kt cos kt transforms into 1 over s squared plus k squared squared. So as a consequence, L inverse of 1 over s squared plus k squared squared equals to 1 over 2k cubed times sine kt minus kt cos kt. Look at the problem backwards, right? Okay, so let's see what the solution. Start from the following, the transform of cos kt. Cos kt transforms into s over s squared plus k squared. Again, we apply what capacity multiply the input function by t. So this one will imply t cos kt transforms into minus the derivative of this with respect to s. Minus d over ds s over s squared plus t squared. Because the derivative multiplied by t is like minus the derivative of Laplace transform to normal usual function. It should be minus. Let's differentiate the quotient, apply the quotient rule with derivative with respect to s. U prime v minus u v prime of v squared. So u prime v is 1 times s squared plus k squared minus u v prime. So minus s times v prime is 2s. So minus 2s squared divided by b squared, a squared plus a squared squared. Okay, so this will be, if you close it here, if you open the, if you just do the calculation here, is k squared minus a squared. With the minus in front is a squared minus k squared over a squared plus k squared squared. That's a partial result. T equals kt transforms into a squared minus k squared over a squared plus k squared squared. Okay. Now let's try to do the transform of this. So sine kt. So from this formula, what we get? Sine kt minus kt cos kt. Transforms into what? Because of linearity here. Sine kt, we know what it is. It's k over a squared plus k squared. T cos kt, we already did it. T cos kt is transformed into this one. So by linearity is minus k times quantity a squared minus k squared over a squared plus k squared squared equals. Let's bring the common denominator, which will be a squared plus k squared squared. And what do we get here? K times a squared plus a squared. So multiply this k, multiply the top and the bottom by a squared plus k squared. So that amounts to multiplying at the top by a squared plus k squared. So k squared plus k cubed. Minus, if you multiply by minus k times what we say here is minus k squared. Minus k squared. Minus to minus is plus k times k times k squared is k cubed is plus k cubed. Which is what? K squared minus k squared, luckily they vanished. And we get 2k cubed. So this will be 2k cubed over a squared plus k squared squared. So what we got here? Sine kt, and write on the final result. It's almost final, but sine kt minus kt cos kt transforms into 2k cubed over a squared plus k squared squared. Then by linearity, we only divide left and right by 2k cubed. We get exactly what written here. 1 over 2k cubed times sine kt minus kt plus kt equals to 1 over 2k cubed on the right, which is 1 over x squared plus k squared. So now by linearity, so this formula includes linearity. So from this one, divide by 2k cubed left and right. There's linearity, so the transformation still holds. So 1 over 2k cubed sine kt minus kt cos kt transforms into 1 over s squared plus k squared squared. So with the consequence that the inverse transform of 1 over s squared plus k squared squared is 1 over 2k cubed times sine kt minus kt cos kt. So we are done with the kind of harder problems from the last latest homework. Now you know how they work. Then let's do some applications. Okay. This so let's try to write down the summary of what we did today, like the harder problems in the homework. So summary. P over 2k sine kt transforms into s over s squared plus k squared squared. 1 over 2k cubed times sine kt minus kt cos kt transforms into 1 over s squared plus k squared squared. And also, I will write the number, so this we could add the Laplace transform of sine kt and cos kt, but we already know. So now applications. Let's try to apply the following problem. Solve the initial value problem, solve the IVP. X second plus x. Again, from this moment on, practically, the unknown function in differential equation is no more y depending on x, is x depending on t. T, the meaning of t, is very close to engineering, t being the time and x being the displacement. So x second plus x equals to, let's do this one, sine t. Let's put the initial conditions, x of 0 equals to 0, x prime of 0 equals to 0. Which are particularly easy initial conditions because the transform derivatives are pretty much straightforward. Okay, so how to do the solution of this problem? Let's do the solution here of this problem. Solve the initial value problem, x second plus x equals to sine t, x of 0 is 0, x prime of 0 equals to 0. So, whenever you solve the initial value problem Laplace transforms, announce your intent of using Laplace transforms. So say, that's how you begin. Say, small x of t transforms to big x of s. Then, apply the formula for the Laplace transform derivative we did prior to this one today. So then x prime transforms into sx minus small x of 0, which is 0. Right? X second will be transformed into whatever as the previous one, s squared x minus small x prime of 0, but it's still 0. So if the initial conditions are all 0, the transforms of the subsequent derivatives or every subsequent derivative requires an extra s. Right? X prime is in sx, x second is s squared x, and so on. And then one more. Whenever we do a differential equation, we must transform also the right hand side. Sine t transforms into 1 over s squared plus 1. Okay, so let's try to transform from a differential equation to an algebraic equation. This is ideal Laplace transform. So s squared x plus bx, capital X, right? Capital X is the most important thing, is the Laplace transform of the function we want to find. So s squared x plus big X equals to 1 over s squared plus 1. Right? Let's give a common factor here, an x times s squared plus 1 equals to 1 over s squared plus 1. What will be x? X will be divide 1 over s squared plus 1 by s squared plus 1 is 1 over s squared plus 1 quantity squared. Now, is exactly the form of interest in this one. We want to find, so that's the solution of our differential equations, but this is exactly x of t, but encrypted. So encrypted means do the Laplace transform. So this is our solution, this is our answer, but encrypted answer. To decrypt it, we have to find the inverse transform. So what's the inverse transform? According to this formula, 1 over s squared plus 1. K is 1 here. 1 over s squared plus 1 squared. 1 over s squared plus 1 squared. Go back is 1 over 2 times sine 1t minus 1t cos 1t. So so small x of t is L inverse of 1 over s squared plus 1 squared equals to, and get here, so to be more readable. So the inverse transform of 1 over s squared plus 1 squared, we apply this formula. The inverse transform of 1 over s squared plus 1 squared is 1 over 2 times sine t minus t cos t. Okay, so we just solved the initial problem. The solution is 1 over 2 times sine t minus t cos t. So let's try to write down here's the problem. And the answer will be for this problem, the answer is small x of t is the inverse transform of 1 over s squared plus 1 squared, which turns out to be 1 over 2 times sine t minus t cos t. We can treat like that. This is a phenomenon of resonance. because if you look at the left-hand side, is x second plus x is the oscillator which the base of solution is cos t and sin t. Now, if the right-hand side can be treated like an external influence on this oscillator. So if the period of the external influence is the same with the proper period of the oscillator, we have the phenomenon of resonance. That means the amplitude of the oscillation is expected to increase linearly. So what's the amplitude of x of t is 1 over 2 sin t minus t cos t. Amplitude of oscillation. A will be so any combination of sin t and cos t is equal to coefficient of sine squared plus coefficient of cosine squared. The square root of 1 over 4 plus t squared over 4, which will be square root of 1 plus t squared over 2. And this goes to infinity. So our amplitude, give or take, increases pretty much linearly because it's approximately with t, right? So that's what we expect. An oscillation which is, for example, it becomes bigger and bigger and bigger. So that's the phenomenon of resonance. Okay. Okay, one more thing. Let's do just a normal initial value problem without resonance. Why is it that Laplace transform of derivatives? Okay, so solve the initial value problem. This is not in the homework, so this is just it's in addition to the homework. So we got solve the following initial value problem: x second minus 5x prime plus 6x equals to e to the power t. X of 0 equals to 0, but x prime of 0 equals to 1. Okay. Solution. Like always, declare your intent of using Laplace transforms. So say small x of t transforms into big X of s. And from this moment on, we'll use small x and big X without, it goes without saying that small x depends on t, big X depends on s. So then x prime transforms into sx minus 0, which is sx. X second transforms into a squared x minus 1, because the next derivative of 0 is 1. Then e to the power t also transforms into 1 over s minus 1. So this is like a dictionary which we use to reformat the differential equation into an algebraic equation, right? These are our dictionary. This dictionary will be used to transform the differential equation into an algebraic equation. That's the philosophy of Laplace transform discussed about at the beginning. So what we got here? X second, s squared x minus 1. This x second. Minus 5x prime, minus 5xx. Plus 6 small x becomes 6 big X. Equals to e to the power t becomes 1 over s minus 1. So let's connect the x's on the left. And the non-x's move them from left to right. So on the left, we got s squared x minus 5sx, 6x, give a common factor x times s squared minus 5s plus 6 equals to move minus 1 from left to right. We get 1 plus 1 over s minus 1. And after a little bit of algebra, it's s over s minus 1. So x times s squared minus 5s plus 6 is s over s minus 1. Solve for x. Big X equals to s over s squared minus 5s plus 6 times s minus 1. And then we can factor completely. We want to use partial fractions. So to use partial fraction, we have to completely factor the denominator as much as we can. So if we factor the denominator, we can get either linear factors or quadratic factors with negative discriminant. So S over S minus 2, S, let me put here S minus 1, S minus 2, S minus 2. S minus 2, S minus 3 is S squared minus 5, S plus 6. S minus 1 is S minus 1. Now, partial fractions. S over S minus 1, S minus 2, S minus 3 is A over S minus 1 plus B over S minus 2 plus C over S minus 3. Clear denominators, we get S equals to A times S minus 2, S minus 3 plus B times S minus 1, S minus 3 plus C times S minus 1, S minus 2. So in the case in which the denominator completely factors in linear factors, different linear factors, right? So it's distinct roots. Then instead of equalizing, we use the method of replacing. So replace S to some special values which will do the job. So those special values here are 1, 2, and 3. If we replace S equals to 1, what do we get? On the left, we get 1. On the right, this is 0. This is 0 because if S equals to 1, S minus 1 is 0. This term disappears. So A times 1 minus 2, 1 minus 3. 1 minus 2 is minus 1. 1 minus 3 is minus 2. Is 2A. So A equals to 1 half right away. So we just quickly get ABC, you do replacing here. The other special value, S equals to 2. So what do we get here? The first factor becomes 0, and the last factor is 0. So we'll get 2 equals 2. On the left, we get the 2. Only this one leaves. B times 2 minus 1, 2 minus 3. 2 minus 1 is 1, 2 minus 3 is minus 1. So it's minus B. So therefore, B equals to minus 2. Okay. And finally, we replace S equals to 3. On the left, we get a 3. On the right, the first is 0, the second is 0. Only the one, this one still stands. C times 3 minus 1, 3 minus 2. 3 minus 1 is 2. 3 minus 2 is 1. So 2C. So C equals to 3 halves. Okay, so basically, capital X is S over S minus 1, S minus 2, S minus 3. After using partial fractions, X will be A over S minus 1 plus B over S minus 2 plus C over S minus 3 with A, B, C already found. Is 1 over 2 over S minus 1 plus minus 2 over S minus 2 plus 3 halves over S minus 3. C is 3 halves. 3 halves over S minus 3. Now, what will be the transform? Now, this is a solution of differential equation in the S space. So it's like an encoded. So it is an S function transformed to get an T function by taking the inverse transform. So then, we already got this one here, so don't need any more. So this is X encoded. There's a Laplace transform of the solution. So from this X, small x of T will be what? Let's transform 1 over 2 over S minus 1. 1 over 2 is a constant. The transform of 1 over S minus 1 is e to the power T. Minus 2, the transform of 1 over S minus 2 is e to the power 2T. Plus 3 halves is a constant, so plus 3 halves. The inverse transform of 1 over S minus 3 is e to the power 3T. So we got a solution of differential equation of the initial value programs. So this is a solution, this is the answer, and the solution of the differential equation, this initial value problem. 1 half e to the power T minus 2 e to the power 2T plus 3 halves e to the power 3T. If you want, let's check x of 0 just for fun. X of 0 is 1 half minus 2 plus 3 halves. 1 half plus 3 halves is 2 minus 2 is 0. X prime of 0 equals to 1 half minus bring down and differentiate minus 4, bring down and differentiate plus 9 halves. What do you got here? 9 halves plus 1 half is minus 4 plus 10 halves is 5, which is 1. It's exactly what we what we already know. This should be like this. Okay, so the situation becomes more complex and more complex as long as we advance through Laplace transforms. So keep in touch and then try to work over the remaining problems in the homework over the weekend. They are due on Monday. So I'll see you around then. So have a good weekend.